In the last lecture, we have defined the notion of a Jordan measurable set, and recall here the definition. A bounded set E, a subset of Rd, is Jordan measurable if and only if the inner Jordan measure is equal to the outer Jordan measure of E. Now we ask ourselves the question is, what kind of subsets of Rd are Jordan measurable? So remember that our main goal was to enlarge the class of objects to which a nice notion of a measure can be defined, and initially we started with the elementary sets of Rd, and now we want to enlarge the class of sets on which a measure can be defined, and this is why we defined the Jordan measurable, the notion of a Jordan measurable set of subset of Rd. Now the natural question is, what kind of subsets are Jordan measurable? So let us begin with a lemma, an easy lemma. It says that if E is a bounded subset and the outer measure of E is 0, then E is Jordan measurable. So the proof is just a one line proof. This is because we already know that our inner Jordan measure is always non-negative. Okay, this is the non-negativity property. Non-negativity. And then we have that the inner Jordan measure is bounded above by the outer Jordan measure of E. This is because, remember the definition of the inner Jordan measure, which is that the inner Jordan measure is the supremum of elementary sets, subsets of E, elementary, and you take the elementary measures of this set A. So now, given that this is less than or equal to, so first of all, so for any subset, elementary subset set A, which is a subset of E, and another elementary set B, which is now a superset of E, we have that the elementary measure of A is less than or equal to the elementary measure of B. This is because of monotonicity property of the elementary measure. Now, if you take the supremum on the left side first over all elementary subsets of E, this is less than or equal to the measure of B. Now this is nothing but the elementary measure of the inner Jordan measure of E. Now on the right hand side, I take the infimum over all elementary subsets which are supersets of E, and this is nothing but the outer Jordan measure of E. Therefore, the inner Jordan measure is always bounded above by the outer Jordan measure. And so now that we know that by non-negativity we have 0 less than or equal to n subscript j, inner Jordan measure of E, this is less than or equal to outer Jordan measure of E, and by hypothesis this is 0. So therefore the outer Jordan measure is also 0. So this implies that the inner Jordan measure is equal to the outer Jordan measure, both are 0. Therefore E is Jordan measurable. E is Jordan measurable. Now let me give a theorem which gives a characterization for Jordan measurable sets. The statement of the theorem is as follows. So suppose that E is a bounded subset of Rd, then the following are equivalent. Okay, so we will give three conditions for the Jordan measurability of E. So first is that E is Jordan measurable. So this is by the definition of Jordan measurability. Second is that given epsilon greater than 0, there exist elementary sets A and B such that A is a subset of E and E is a subset of B, and the elementary measure of B minus A is less than or equal to epsilon. So this second condition says that the set E can be sandwiched between two elementary sets A and B such that the difference B minus A has elementary measure as small as we like. So this says that the difference between the inner approximation and the outer approximation can be made as small as we like. Now the third condition says that given epsilon greater than 0, there exists an elementary set F such that the outer measure of E with the symmetric difference of F is less than or equal to epsilon. So here note that this F may or may not lie completely within E, or may not cover E completely as well. So we take the symmetric difference, but it says that the outer Jordan measure of this symmetric difference is as small as we like. Okay, so let's try to prove this. So proof. So first is we will show 1 implies 2. Now by Jordan measurability, so we know that from 1 that the set E is Jordan measurable, and we will produce two elementary sets, one inside E and one covering E, A, B elementary, such that, so let us fix first an epsilon greater than 0, and given this epsilon we have to find A and B elementary such that the measure of B minus A is less than or equal to epsilon. So let us start with the definition of inner Jordan measure. So by definition of inner Jordan measure, we have that there exists an elementary subset of E such that the inner Jordan measure of E is less than or equal to m of A plus epsilon over 2. Now this is simply by using the property of the supremum, using the definition of supremum. So we can find an elementary subset of E such that the inner Jordan measure is less than or equal to the elementary measure of that subset plus some epsilon over 2. Similarly, by definition of outer Jordan measure, there exists an elementary subset B covering E such that the outer Jordan measure of E is greater than or equal to MB minus epsilon over 2. Now this is just using the definition of the infimum, using the definition of infimum. Okay, so now we can write, let's start with this one here. So MB minus epsilon over 2 is less than or equal to M superscript E, J of E, so our outer Jordan measure of E. But now we know that since E is Jordan measurable, these two, the inner Jordan measure and the outer Jordan measure, are equal. So by Jordan measurability of E, and next we have, from the first inequality, we have MA plus epsilon over 2. So if we consider the first term in this chain of inequalities and the last one, then we have what we want. So this implies that MB minus epsilon over 2 is less than or equal to MA plus epsilon over 2. So all these things are finite, so you can not finite and non-negative, so you can subtract on both sides. Is less than or equal to epsilon, and because A is a subset of B, we have the measure of B minus A is equal to measure of B minus the measure of A. So this is what we wanted. So this proves that E is Jordan measurable, implies that there exist elementary subsets A and B, one within E and one without, covering E, such that the difference has measure as small as we want. Okay. So now we can go to the second part. 2 implies 3. So here we know that given epsilon, there exists A and B again, such that the measure of the difference B minus A is less than or equal to epsilon, and we have to show that there exists an elementary set E, elementary set F of RD, such that the outer Jordan measure of the symmetric difference is less than or equal to epsilon. So again, so we fix here an epsilon, and then we can say that there exists an elementary set F for which this is valid. Okay. So now the obvious candidate to choose is F equal to B. So consider this set B itself, then the symmetric difference is simply the union of E minus F and F minus E, but since E is a subset of F, then this implies that the symmetric difference is simply the difference F minus E. So this is because we have chosen F to be our set B. Okay, and now since A is a subset of E, F minus E is a subset of F minus A. Okay, so we can just write this as F intersection E complement and this as F intersection A complement, and this inclusion implies that E complement is a subset of A complement. So therefore this is F minus E is included in F minus A. Now by the definition of the outer Jordan measure, so if you take the definition of the outer Jordan measure of the symmetric difference E of E and F, this is nothing but the outer Jordan measure of F minus E because of our choice of F, and then this is less than or equal to measure of F minus A, because this set is now elementary, and by the definition of the outer Jordan measure, this is the infimum of all such sets. Therefore this outer Jordan measure of F minus E is less than or equal to the measure of F minus A. But since F was equal to B, this is B minus A, and we know that this is less than or equal to epsilon. Okay, so this shows that 2 implies 3. Now the most tricky part is 3 implies 1. It is not too difficult but a bit tricky. So here we know that given epsilon greater than 0, we have an elementary set such that the outer Jordan measure is less than or equal to epsilon. So we choose for given epsilon such a set F. Now we need to show that the difference difference between the outer Jordan measure and the inner Jordan measure is less than or equal to epsilon. So since epsilon is arbitrary, this would imply that these two things are equal, and this is the same as saying that E is Jordan measurable. Okay, so we start with what we know, which is that there exists an elementary set F such that the outer Jordan measure of the symmetric difference of E and F is less than or equal to epsilon. So by definition of outer Jordan measure of this symmetric difference, so again let us fix our epsilon. So once epsilon is fixed, we choose our elementary set F, and then we can say that by the definition of the outer Jordan measure, there exists an elementary set, let us call it S, such that the outer Jordan measure is greater than or equal to the measure of S minus epsilon over 2. So in fact it will be convenient to have already that the outer Jordan measure is of E symmetric difference F is less than or equal to epsilon over 2. So then we have this is less than or equal to epsilon over 2. So let us look at the Venn diagram picture that we have here. So we consider our set E in blue and our elementary set F in violet color, and now this part is E minus F. So this is E minus F, and this part is F minus E. This part is F minus E. Now our set S will cover the union of these two. So it can be something like this. So one part covers E minus F and the other part will cover F minus E. So it could be something like this. So the set S will be a union of these two regions enclosed in the green boundaries. Now if you consider F minus S, so which is simply F intersection S complement. So S complement will have two parts. One part is within E intersection F and the other part is without. So this is outside E union F. So I will consider the part which lies only within E intersection F, which is why I have taken an intersection with F. So one can easily show that this is inside E intersection F. So as an exercise, you can check this using just the laws for intersection, union and complements. You can simply show that this lies within E intersection F. Therefore, the elementary measure of F minus S is less than or equal to the inner Jordan measure of E, because the set F minus S is an elementary set which lies inside E intersection F, so it also lies inside E. And so by the definition of the inner Jordan measure, we have this inequality. So I am going to write this as minus MJE, the inner Jordan measure, is less than or equal to minus measure of F minus S. Now consider the union of F and S. Now one can show that this is this includes the set E itself, because S covers E minus F and union F minus E. So one can check again that this set F union S covers E, and now this is again an elementary set. So therefore we can use the definition of outer Jordan measure of E, and this will be bounded above by the measure of F union S. So this implies that the outer Jordan measure minus the inner Jordan measure of E is less than or equal to measure of F union S minus measure of F minus S. So this thing was less than or equal to this thing, and we have added the two inequalities. Okay. So now notice that this right hand side is equal to the measure of S itself, because F union S can be written as S union F minus S, and this is a disjoint union and one can use finite additivity to get this equality from m of f union s minus measure of f minus s is equal to measure of s, but s was chosen to have measure less than or equal to epsilon. So, we have shown that outer measure of E minus the inner measure of outer Jordan measure of E minus the inner Jordan measure of E is less than or equal to epsilon, which shows that E is Jordan measurable. So, these extra two equivalent conditions for the Jordan measurability of E will come in quite handy to prove if some given bounded subset of RD is Jordan measurable or not. Now, we will use these equivalent conditions to show some nice properties of the Jordan measurable sets, which it inherits from elementary sets.